Everyone, welcome to our IB Physics HL first online lesson. Today we'll be learning about refraction. This is Mr. Keppel, and today I'm joined by, in voice chat, who's here with us? Say hello. Who is that? Kong's here. Is anyone else in voice chat today? Alberto's here. Awesome. If anyone else pops in, gets your mic working, just say hello as soon as you get it working. Thanks for joining, you guys. I'm really glad you could be here. And make sure that we're saying hello to everyone else who's watching this later on YouTube. All right, so I just want to let you guys know, this is weird. Online teaching is not something that we're used to. So I wanted to give you guys the option of joining live while I'm teaching. And if you can't, that's fine. You can just watch it at a later date. But basically what I'm going to do is you'll have a choice of how you want to learn. So you can either come watch the live stream, you can watch a recording of the live stream, or the third option is you can just read a textbook. And I'll be posting all of this on Google Classroom. I'm going to record it first, then I'll post it on Google Classroom. So you guys that are recording now, nothing is on Google Classroom yet. The idea is that you're going to have a choice of 3 ways that you want to learn, and then you'll have a choice of 3 ways that you want to demonstrate what you've learned. And I'll give you more information about that when I post the assignment on Google Classroom. But essentially, you can write me a little written reflection on what you learned. You can make blog posts or social media tweets, or do a Zoom video with a friend where you're just kind of talking about these things. You can design a presentation for me. You can do all sorts of stuff, but the rule is that you're not supposed to spend more than 20 minutes on it. But I just want you guys to know that you have a flexibility on how you want to show me what you're learning and how you want to learn. And the whole idea is all of this is optional. I can't give you guys a grade on any of this stuff. So it's just about learning and trying to make sure that you're filling in what would have been a large gap in your education, so that we're continuing this learning process. It's not going to be perfect. What questions do you guys have for me about this process? We good? How are we feeling? How about that? How are we feeling? You're fine. Okay, good. Alberto, how you doing? You guys excited to learn some physics? Let's do it. All right, the way every online lesson is going to work is I will have 3 main ideas that I'll be trying to teach you each day. So for today, the main ideas are as follows. We want to know the refractive index of the material relates to the speed of light in that material. There's also this equation over here. This is a review of where we left off. I just wanted to kind of start with something I've already taught you because it's going to be a weird transition. The second main idea is that Snell's law relates the angle of incidence to the angle of refraction. And so that's Snell's law there. And then lastly is this concept called total internal reflection. And it occurs when all of the incident light is reflected off the boundary. So as you remember, the way refraction works is when light or wave changes from one medium to another. So here we see this beam of light is incident coming in, and it hits this piece of glass. And when it hits it, I guess I should be drawing. Yeah, it's going to hit the glass. Normal would be like that. Normal is always perpendicular to surface. And then the beam bends. Instead of continuing on that straight path, the beam bends and goes off to the side. And then again, it hits over here, and then it bends one more time this way. So every time that the light changes mediums from air to glass and then back to air again, every time it's changing mediums, the path of light is bending. And we call that phenomenon, we call that refraction. To make it a little bit more technical, we come up with these terms called the refractive index, which tells us roughly how optically dense the medium is. And so every different material will have a different refractive index. And then we talk about the normal, which is the perpendicular to that boundary. I don't know why it just did this. Oh, it's because someone just added me. Can you add Michael? Michael? And right, what are you talking about? Who's Michael? Con, can you explain this? Oh, they're not. Okay, so I have to go up to the lobby and add them. All right, thanks. Okay, Eddie, H, and Ryan. H. Okay, we good now? Hopefully they'll see that. Okay, so apparently when you at me on Discord, it pulls me out of my OneNote. Oh, or my OneNote crashed. I think my OneNote crashed. Technical difficulties. We're doing this live. All right, so maybe you guys remember a lot of this. Like we talked about how the ray comes in, and now we call that the theta 1. That's the angle of incidence, and it's going to hit the boundary, and then it's, instead of going straight through, it's going to bend, and then we have theta 2, which is the angle of refraction. All right, what's up? Okay, I have this link to a list of refractive indices, so I'll pull this up. Chrome, yeah, use Chrome. This is Wikipedia. I'm going to be using a lot of stuff from Wikipedia today, but if you click on this link, or if you go to this website, list of refractive indices on Wikipedia, it'll just show you a bunch of different materials, and it'll tell you the refractive index of each of those materials. And so remember that this number is telling you how optically dense the material is. The higher this number is, the more dense the material is, and the slower light will travel through that material. So just thought it'd be cool, you guys can see this list of all these crazy materials that and how fast light travels through them. So the refractive index is often also called the index of refraction. In America, we tend to call it index of refraction more so than refractive index, but you'll hear both those terms interchangeably used. I don't have my webcam being displayed. There it is. Okay. It's a dimensionless number, which means it doesn't have any units, and it just basically describes how fast light travels through the material. This is the equation that we use to relate those together. I feel like this text size should be a little bit bigger here. How do I change that? Maybe like 26. There we go. All right, so in this equation, n is the refractive index, c is the speed of light in a vacuum, 299, 792, 458 meters per second, and then v is the wave speed in the material. So here's an example question. The refractive index of water is 1.33. Remember, it's dimensionless quantity. There's no units on there. So the question is, how fast does light travel through water? So we look up at the equation, and we basically need to solve this equation for v. So we're trying to find how fast it's traveling. So we're trying to find v. So what would v be? V would equal... Are you guys still on voice chat? I feel like I'm talking to myself here. So what would I put for v? It would be... If I rearrange this equation to solve for v. No one's going to say anything. I'll just pretend I'm by myself. How about that? So it's going to be... It would be C over N. Is that Anna? I'm so happy you're here. Okay, so now I'm going to put the speed of light, which we usually write as 3 times 10 to the 8th. And I'm going to divide it by the refractive index, which is 1.33. I don't know if you guys have your calculators out with you. I will... Let's see, which calculator should I use? I'll just use the Windows calculator. That's fine. So I want to take 3 divided by 1.33, and I'll get 2.255. So 2.255, and that's times 10 to the 8th power. And so that's the speed of light in water. So if we compare that to the speed of light in a vacuum, it's a little bit slower. And so the reason it's slower is because the index of refraction is greater than 1. So when you're traveling through a vacuum, in this equation, you'd have the speed of light in a vacuum would be v, and then c is the speed of light in a vacuum. And so you'd have the same c and the same v, and you'd end up getting n equals to 1. So basically, anytime n is greater than 1, you're going to be going slower than you would through a vacuum. So that's how you can use this equation to calculate the speed of light in a medium. What questions do you have about that? Is that making sense? Okay, I'll move down. Question 2. A wave transmits into a medium with twice the refractive index. By what factor does its wavelength change? So this is kind of weird, right? Because the equation we were just looking at, it was n equals c over v. But I don't see wavelength in there. So where would we find the wavelength information in this equation? Any ideas? So n is a dimensionless quantity. It's a constant value for each material. C is a constant value, speed of light in a vacuum. So where could the wavelength of the wave be? Well, there's only one choice. It has to be inside the speed. And so you guys remember that there's an equation that tells you the wave speed. Do you remember what it was? It's the wave equation. It's v equals... You guys don't remember it. It's been weeks. The world has gone to hell, and we don't remember anything about physics. It's lambda f. So we can combine these two equations. We can take the wave equation and we can take the index of refraction equation and stick them together. And so what would happen? So if we do that, we'll end up with n. So this would turn into n equals c over lambda f. So now let's see if we can go back and answer our question. So what we said was it's changing into a medium with twice the refractive index. So this quantity here is going to be doubled. And it wants to know by what factor does the wavelength change. So if we isolate just those two, we would have n is proportional to 1 over the wavelength. So the speed of light in a vacuum, that's c, and the frequency of the wave is not going to change. Only the refractive index and the wavelength are going to change. So what would happen if the n was doubled? What would happen to lambda? So if we plug in a 2 for the n, then that means that lambda would be, what would happen? You guys with me? No one's here. I'm going to check on Discord. 1 over 4. My screen turned black. Check request. What does this mean? We're here. All right, I'll just keep going. If you guys want to jump in, you can. So basically, it's just going to be 1/2. So if you go to a material where the index of refraction is twice as large, that means you're going at half the speed. And so your wavelength will be half as much. So if you think about a wave as it's traveling past, if the wave travels slower, the wavelength is going to get more squished. So if a wave is going fast, it's going to be like, shoom, 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 shoom. It's going to have that really stretched out wavelength. Whereas the wave is going slow, the wavelengths are going to be more squished together. So if the index of refraction is doubled, your wavelength is going to be half as much. So there's a relationship not just between the index of refraction, or the refractive index, and the speed, but there's also a relationship between the refractive index and the wavelength. Question 3. A wave transmits from a material with a refractive index of n1 to material with a refractive index of n2. Determine the ratio of the wave speed in material 1 to the wave speed in material 2. Okay, so we know that we're going to be, I'll draw a little picture here. So let's say, I'll do it this way. So let's say that our wave is starting out up here in material 1. So I'll call this N1. And the light beam comes in, and then it's going to hit this boundary, and then it's going to refract. I'll just make it refract that way. It's going to refract into N2. So the question is, what is the ratio of the wave speed in material 1? So what's the ratio of V1 to V2? So if we think about our equation, N equals C over V, we're trying to find the ratio of V1 to V2. So if we solve this again for V, we get that V is equal to C over N. So what we have is we have V1 over V2. That's our ratio of the velocity of material 1 to the velocity of material 2. So we just have to take our C over N and just plug it in. So we're going to have C over N1 divided by C over N2. And since the C is the same, it's the speed of light in a vacuum, it's going to cancel out. And then we get that V1 is equal to, and now because it's 1 over N1 over 1 over N2, the N2 on the bottom is going to come up to the top. And so you're going to have N2 over N1. And so that's a good thing to know is like, because there's an inverse relationship between the index of refraction and the speed, if you want to find that ratio of the speeds, it's going to be the reciprocal of the ratio between the refractive indices. I'm going to pause to see if you guys have questions. I'm going to go check the Discord. All right, looks like a lot of you guys are having issues with your mics on Discord. Look how many of you showed up. Jeez, this is way more than the number of you that voted for synchronous learning. I can hear you, Ryan. Yeah, we can hear you now. Great. Sorry for all the mix-up, but this is exactly why I wanted to go over a lesson I'd already taught you guys for the first time that we're doing this. So hopefully maybe we can like try to schedule a time where we jump on another time when I'm not teaching, and then we can try to see if the mics are working and stuff like that. I recommend you guys try to pop into one of my office hours to try to see if you can get your mics to work. So I'm going to keep going. I got 15 minutes left. We'll see if I make it or not. All right, so now I want to talk about Snell's law. So Snell's law is this equation. I'm not going to derive it for you because it would require calculus. You could go on YouTube and probably watch some awesome derivations of this. So the Snell's law basically is that the refractive index of material can also tell you by how much the path of the light is going to bend. And so Snell's law describes this to us. So this is Snell's law. It's n1 sine theta 1 equals n2 sine theta 2. We already talked about what n is. It's the index of refraction of the material. So now we need to understand what theta is. So we can look at this picture over here. So theta 1, that's your incoming angle. And we always measure the angle to the normal, which is perpendicular to this interface. So the normal is always perpendicular, which is why we use the word normal for that. So theta 1 is your incoming angle coming in, and then theta 2 is the refracted angle after it transitions through the boundary and through this interface and it changes the mediums. We want to express this equation two additional ways. So in the IB data booklet, they're not going to show you this equation. They're not going to show it to you like this. They're going to express it in these different ways. So let's express this as a ratio of the refractive index of each material. So we can solve this for n1 over n2. So n1 over n2. So what would happen is I would just need to take this sine theta 1 and just move it over there because I've taken this n2 and I moved it over there. So you'd end up with sine theta 2 over sine theta 1. And that's how the data booklet's going to write Snell's law. So I like this way up here, writing it out in a line, n1 sine theta 1 equals n2 sine theta 2. I think it like kind of flows better and I can remember it better. But the data booklet, for whatever reason, expresses it this way. We could also think back to up here where we said that n2 over n1 is v1 over v2. And we could replace this n1 over n2 with a velocity ratio. But we remembered that up here we found that the ratio of the velocities is the inverse of the ratio of the index of refraction. So instead of n1 over n2 being, so over here you can see it's n2 over n1 is v1 over v2. So we're going to have to flip that around. Since this ratio is flipped, we're going to have to flip this one. So it'd be v2 over v1 equals sine theta 2 over sine theta 1. And this is how the data booklet will write it out. They'll actually, in the data booklet, if you look it up, it actually has an equal sign here and it says v2 over v1 on it. So that was why I showed that to you guys up here, was so you can understand what the data booklet's doing. All right, this is boring stuff. I want to get to the cool stuff. I have so much awesome things planned here. All right, so let's do some questions on this. So number one, draw a diagram and apply Snell's law to show that when theta 2 is less than theta, show that theta 2 is less than theta 1 when n1 is less than n2. So let's label those. So this is going to be theta 1. This is going to be theta 2. And so all that we want to show, and my thetas are like super diagonal. I'm writing at a weird angle here. It's fine. I'm not going to change it. We just want to show that what's happening here is you're going from air into water. And so air, the n is approximately 1. It's like 1.00 something. It's nearly 1. And in water is 1.33. So this is n1 and this is n2. So we have exactly that. We have n1 is less than n2. 1 is less than 1.33. And so we want to show, indeed, that this picture is correct. We want to show that the theta actually decreases when you transition. So if we look at our equation, n1 sine theta 1 equals n2 sine theta 2. What we want to do is solve this for theta 2. The way to solve this for theta 2 is we first want to rearrange. So we just have sine theta 2. We're going to divide both sides by n2. So we'll have n1 over n2 sine theta 1. And then we want to solve, we want to get rid of this sine over here. So we need to take the arc sine of both sides, or the inverse sine. And I'm going to get n1 over n2 sine theta 1. All right, so now what we set up here was that n1 is less than n2. So what's going to happen down here in this ratio, if n1 is less than n2, then what are we going to get for that coefficient in front of the sine term? We're going to get a number that's, if n1 is less than n2, we're going to get a number that's less than what? Anyone? If the top is smaller than the bottom, the value must be less than 1. You got it. And so the way that the inverse sine works is if you have a number in there that's less than 1, right, you're going to end up shrinking. You're going to end up shrinking that angle. And so we can see that since n1 is less than n2, you're going to get a number less than 1 there, and it's going to end up shrinking down that angle. That's kind of like a qualitative answer, but I don't really have time to go into the trig on this. But basically just that because that ratio ends up being less than 1, you end up shrinking the angle. And so this kind of makes sense because what's happening is you're going from a medium where the light's going really fast and you're transitioning to where it's going slow. And so it ends up bending towards the normal. And so that's what we say. We say that when you go from fast to slow, you bend towards the normal. So I'll write that down. So bend towards the normal. So the question is, what if we flip that around? So what if the what if the light, instead of starting in the air, actually started in the water? So what would happen if we came up the opposite direction? So what would happen there? So now this would be our N1, and then this would be our N2. And N2 is approximately 1, but N1 is 1.33. So now when you look at that ratio that we had up above up here, N1 over N2, what's going to happen now? That N1 over N2 ratio is going to end up being 1.33 divided by 1. It's going to end up being greater than 1. And so what's that going to do to theta 2? So that means that theta 2 will increase. And our theta 2 is this angle here now, where this is our theta 1. And so we say that when you go from a optically dense material, where the light travels slow, into a less optically dense, I don't know what to say for that is, thinner, it's going to go faster. And so when the wave speeds up, it's actually going to go away from the normal. And so here we say it bends away from the normal. So those are just two things to kind of keep in mind. It'll really help you out when you're looking at these problems, is just think, all right, if it's slowing down, then the angle is going to decrease. If it's speeding up, then the angle is going to increase. And if you can just kind of track that, and that makes sense, like just establish that as your baseline, solving these refraction problems will be a lot easier for you because you'll have like, signposts to kind of like logical things that will kind of guide you through it. All right, here's an example problem that I thought would be really cool. I got this. This is the image source here. It's from Wikipedia. It says calculate the refractive index of the material shown in the picture below. Okay, so what we have is we have a laser shining down here. So the beam is coming, man, I'm like covering my camera with my hand. Sorry guys, I'm having trouble drawing on my surface. Okay, there. So the beam is coming in this way. It's entering, it looks to be glass. Maybe it's plastic. There's some material here that it's hitting. And then what's happening is we can see that instead of going straight, that the light is bending. You'll also notice that there's a little bit of a reflection here as it reflects off the boundary. That happens as well. And then we call this the transmitted ray. So we want to figure out what the refractive index is of this object here. We want to figure out what its refractive index is. So that's going to be, I don't know, I put an arrow there. This is going to be N2, and then N1 is just error. So we'll just use 1. So here's what we know. We know that N1 sine theta 1 is equal to N2 sine theta 2. Well, we know what N1 is because we just said that N1 is error. So we're just going to leave that as a 1. We know what theta 1 is. We can read it off the diagram here. So that's 60 degrees. We do not know what N2 is. That's the unknown material. But we do know what the refracted angle is. It's this angle right there, which if we zoom in on it, if this is where the 30 is, then we are approximately at 35 degrees right there. So I'm going to have sine of 35 degrees. And now I'm going to have a problem that I can't do with the Windows calculator, so I'll have to, I hadn't thought about this. So we're going to take sine of 60 divided by sine of 35. And I think I have a calculator on my desktop. Let's see. There it is. Hey, look, it's Dominic Wallingman. Okay, let's see. So I'm going to take sine of 60 divided by sine of 35. And I hope I'm in degrees. 1.5. That is the correct answer. So that I can tell you right now that this is glass. If we look up on our list of refractive indices, let me see if I can find glass. Search for glass. There you go. So a form of pure glass, 1.5. So there you go. So that makes sense. So now, like, this is really cool because by just staring, my webcam's gone. by just staring at this picture, we were able to figure out, based on how the light bent as it went through the material, we were able to figure out what this material was. That's cool. That's awesome. That's like, that's physics. How much time do I have? I have 5 minutes. Okay, let's keep going. Number 4. Suppose the angle of incidence in question 2. Okay, suppose the angle of incidence. So suppose this angle is gradually increased. Explain whether there's a limit to how large the angle of incidence can get for which the light still transmits through the boundary. Okay, so what's happening here is, like, if this angle were to be increased like this, then we would bend even, I should use a different color. If we were to increase that angle, then what would happen is you would bend even more away. Your angle of refraction, like this outcoming angle, would become even greater. And so eventually you can see that there is going to be a limit. And that limit is when the angle that comes out is exactly parallel when it's 90 degrees. So the limit is that theta 2 cannot exceed 90 degrees. So whatever theta 1 is, it has to be a value that does not allow theta 2 to go past 90 degrees. So we're limited because you can see, like, what has to happen is when you're going from a material where light is slow to one where light is fast, so from water to air, for example, then the light's going to have to bend away from the normal. And it can't bend more than 90 degrees, because if it went past this 90 degree, it would be back in the water again. And so it said that we want to find the limit where the light could still transmit through the boundary. So this is the hard limit, and we end up calling this the critical angle. So critical angle is theta 1, which gives theta 2 equals to 90 degrees. My thetas are so disgusting, whatever. So that's called the critical angle. All right, now fun stuff. I got 3 minutes to show you guys fun stuff. So here's a visualization of this. I got this off this hyperphysics page over here. You can see that as the angle of incidence is increased this way, you can see that we're getting more and more to the point where now we're at that 90 degree. And then what happens past that is something that's called total internal reflection, is that the light actually cannot transmit and it gets entirely reflected back in. And so that's why this angle here, that's your critical angle, where you've hit that 90 degree refraction angle, and now you can no longer refract, you can no longer transmit through, and everything gets reflected back in. So here's a really cool video of this that I stole from Dustin at Smarter Every Day. This is an awesome video. Are you gonna play? Okay, here you go. Oh, it's lagging so bad. Let me try this one more time. Oh, that's disgusting. Okay, here we go. All right, so he's got this laser. It's underneath water. And so he's slowly increasing the angle of the laser. And now there's your total internal reflection. But once he hits the critical angle, it stops internally reflecting. My computer cannot handle playing a video. My Surface cannot handle playing a video and recording my own video and sending this to you guys over the internet all at the same time. So this creates this really cool phenomenon for if you're an underwater diver. It's called Snell's window. And so here's a picture of that. And you can see that there's sort of this area here beyond where it's dark. And so what's happening is that none of the light from above can reach you. So here's a picture of that. So what happens is you're down here, like this is your eyeball. And so you're looking up towards the surface of the water. And what's happening is when you look at these angles out here beyond the critical angle, you're only able to see you're seeing all this light that was underwater reflecting back to your eye. So when you look over at this picture here, all of the light that's outside of this window, this like 360 degree window, is the window of the critical angle. And so all the light that you're seeing from beyond that point is internally reflected from the bottom of the ocean. And so that's what's making it look all like black and stuff like that. So like divers call this Snell's window. Here's another example of this also from Wikipedia. This picture of this woman underwater. It says total internal reflection by the water surface at the shallow end of a swimming pool. The broad bubble-like apparition between the swimmer and her reflection is merely a disturbance of the reflecting surface. That's this bubble here that they're talking about. Some of the space above the water level can be seen through Snell's window. So this is where the Snell's window is. So you can actually see above the water from that window, but everything else down here is a reflection of what was under the water, bouncing off the surface and reflecting back down because you're viewing at an angle that's greater than the critical angle. Oh, I'm out of time. So sad. Here's the video. You guys can go check it out. I'll link to this in the Google Classroom assignment. But this video is just absolutely amazing. You guys totally need to go watch it. So this is the question down here that my time's up. This is the question that I'm gonna leave for you guys to figure out to demonstrate your learning. I'm gonna go through it here, but I'm basically done. You can turn off the video now. I'll post all this on Google Classroom. It says a laser pointer is held horizontally underwater and initially sends out a ray horizontally. The laser pointer is then gradually rotated so the beam points more towards the normal. Realize that the normal is, so that's your normal right there, the 90 degree to the boundary. It says, determine at what angle to the normal the reflected beam will no longer be visible. So you want to figure out at what angle, so you can see right here, boom, you want to figure out what that angle is, what angle does he need to hold the laser at so that you can no longer, so it's no longer reflecting back down. So that backwards down reflection is stopped. That's the critical angle essentially. So that's the problem that I want you guys to figure out. Have fun with it. Make sure you ask me questions on Discord if you need help with anything, or on Google Classroom. But I'm going to stop the video now. If you guys want to chat after this, it's great. But I'll see you guys later. Making sure I stop.